Let's start with another topic, that is short circuit of a synchronous machine on no load. When there is a no load on a synchronous machine, that time what happens, it works under a steady state condition. When you start a generator, the generator will be giving the power without any interruption or without any fault. You receive the supply from the generator uninterruptedly and without any change in the power system. This is there. But short circuit occurs, if short circuit occurs, then it creates lot of problem. Now let us see with this one diagram what will happen in this one. So this is the diagram. Okay, this is the diagram. Now in this one what happened, there are many things, that is leakage reactance. When any transformer is there, for example this is a transformer circuit diagram. We have taken transformer circuit diagram. In this one, uh, if you see the first one, that is 9.3a, first one, that is steady state short circuit model. When a synchronous is operating, that time synchronous is operating, a synchronous generator consists of a resistance, it consists of a reactance inside the winding consists of both the things, resistance it consists the reactance also. So we have to consider. Now let us consider only the reactance. Now during the normal condition or steady state condition, current will be flowing, there will be no changes, generator will be working as it is. When any fault, three phase fault or line to line ground fault, symmetric fault, asymmetric fault, any of the fault occurs in the generator or near the generator, lot of changes take place. The current increases, the value of the current increases to maximum value. When it increases the maximum value, the fault is transferred to the generator armature winding. That armature winding, what happened, it is transferred to the armature winding. So when the high current it is transferred to the armature of the generator, then automatically the flux also increases in the machine, in the armature it increases in the machine. So this is the condition, first condition, that is 9.3a, figure a shows the condition when a short circuit occurs. XL is a leakage reactance, xa it is called as the armature reaction. So when heavy flux start producing in that one, it tries to neutralize, it tries to reduce the flux, that is the armature reaction, it is called as a armature reaction. Then what happened in this condition, the next condition, what happened in this, if you see this next condition, this is the next condition. In next condition, that is subtransient. Now three state will take place. It comes, fault occurs, when a fault occurs, it comes in a three state. First it comes in a subtransient, where very heavy current increases. Then come transient means what happens, it slowly reduces. Then it comes the steady state. Now in this transient, in subtransient, when this heavy current is induced in the armature, then flux will become more. When the flux will become more, then it has to be contracted, counter reacted, and it has to be reduced, the flux has to be reduced. To reduce the flux, that time what happened, field winding, damper winding, these both windings inside the machine, generator machine, start working. It takes the flux, it also induces the flux and tries to neutralizes the main high fluxes. So they come in picture, they come in parallel. So the reactance of a damper winding, field winding, and reactance of armature, this all come in parallel with the leakage reactance. This is during subtransient period. Next what happens, next is that it is a transient period. During the transient period, the flux, damper winding flux, little damper winding flux, damper winding reduces the flux, it reduces the flux to a larger value, it is reduces the flux to a larger value, and then it decreases the main flux, so automatically it gets reduced. Now in this one it gets reduced. Now if you see only two fields, two windings inductance, two reactants will be in the parallel. One is field, One, if you see, one is a field winding, another one is a armature winding. They comes in the they come in the picture, or they come in the parallel. The damper winding has no it doesn't reduces the main flux, because already it has reduced the current from subtransient to the transient state, so it reduces. Only two comes in picture. Now for this we have to take a parallel this all three. For example, what you have seen, x dw x f x a, this all comes in the parallel. So we will represent this in the parallel way. See, if you see this one, we are representing them in a parallel. This comes in a parallel. If you see, they all are comes in the parallel diagram for the subtransient. This is for subtransient. For transient, what happened? X dw decreases, it becomes 0. So for subtransient, for the transient, what happened? This diagram for this one will come. X dash d is equal to xl plus xa parallel to xa for this one. For this also, if you see for the transient, for example, for if you see for this steady state, then what happens? Steady state, we see only xl will be there, only xl. There is a no armature reaction will not be there for this one. So this is the thing how it comes. This is a diagram which shows how the things will be working. If you see this one diagram, the current increases to high value during the fault condition. When fault occurs, it goes to a very high value. First it will be in subtransient mode, where the current will be very high. What happen then? Reaction, armature reaction and damper winding, they come into effect, they come into action and reduces the current, reduces the flux of the current during the subtransient period. Now what happen? Afterwards it get reduces, the flux inside the armature or inside the generator reduces. When it reduces, it goes to the next state, that is called as a transient. Transient you can find only armature reaction, but the size or the magnitude of the current here, it is a more. So again armature reaction come into effect, and what happens? It tries to reduces again the flux, the high fluxes to a steady state, to a normal condition. Then after reducing, it reduces, next it turns to a steady state period. After few cycle, it comes to a normal condition. Normal condition is called as a steady state period. Now in this one, what happened? Circuit breaker also is very important. Circuit breaker plays very important, because what happened during a short circuit of a synchronous generator, there is lot of changes. The current increases. Some DC offset current also appears in three phase. DC offset current also appears in the in the phases. So they have to be checked, and the particularly calculation has to be done to find out the maximum current which a circuit breaker can withstand. Because what happens when fault occurs, the current will increases. When the current increases, circuit breaker has to has to withstand that fault current. Now here you can see this one, particularly if you see the another oscillograph, see the steady current. If you can see the, this is a steady current or change, how it changes take place. This is a steady magnet amperes. First it increases, again it goes back to the steady state current. The next topic is short circuit of a Lotus synchronous machine. Now till now we were working on a synchronous machine which was with no load. Now let us see what happens when a short circuit occurs when the synchronous generator is loaded. Now you can see this one already. Now you are seeing a diagram. This is a circuit model of a loaded machine. That is, EG is a generator, X XD is a direct access synchronous reactance. It is called as a synchronous reactance. I naught is a load current, and V is a terminal voltage terminal. Now when it is, this one diagram shows when it is working at a normal condition. When things changes, when any fault occurs, when a fault occurs, then that time it goes into a subtransient mode, then transient mode, and steady state. So this is the condition when the things happen. This is the condition. Now see, it goes in this condition. Now it goes in subtransient, it goes in the transient. So we will replace with all the things for subtransient, eg double dash xd double dash, that is subtransient, I not same, and this is a transient. So it goes in subtransient, again after few seconds it comes to a transient method. Now I have to convert this one into a another equation. That use, this is the equation, we can show this one is the equation. Okay, this is considered, that is uh, e subtransient, eg subtransient v naught plus j I load current into x double d, that is a, now this is e dash g is for a transient, for it is a use for the transient one. So this equation what you are saying, this equation, it is nothing derived from these two particular circuit model using Thevenin's equations. Using Thevenin's equation we will derive that one. Now this is for generator, and if it is a motor, it changes, the equation changes, instead of plus minus occurs here. Selection of circuit breaker, it is very important topic. So how we are going to select a circuit breaker? Circuit breaker is very important, but selection of a circuit breaker depends upon the rating at the maximum, rating at the operating condition, and rating at the maximum when the fault occurs. When the fault occurs, the rating differs, and at the normal rating, the rating differs. So uh, it requires rated momentary current and rated symmetric interrupting current. Rated momentary current is normal current. It is a normal current when which they take, and which will be working at the steady state condition or normal conditions. Now symmetric SC current is obtained by subtransient reactance. When we calculate, subtransient reactance is the highest or maximum value of a current, or the maximum value which the current which the amplitude or maximum value the current we are going to obtain, that is the maximum value we are obtained. Symmetric SC current is obtained from that one, from subtransient. From the subtransient we have taken, and momentary current we are taken by multiplying factor 1.6. Okay, 1.56. So there are now this is a circuit breaker, which shows the number of a cycle, a multiplying factor in how many cycles you want to break or open the, sorry, you want to open the circuit breaker, that they have given cycles, and this is the multiplying factor they have given. So and some formulas have been given to calculation, that is very important. The main thing, we have to calculate short circuit MVA current. Short circuit current, when a short circuit occurs, that time current increases. Current may vary, line to ground SC may short circuit current may be differ. Ground to double line to line fault, SC, that is short circuit current, differs. When three phase fault occurs, short circuit current differs, that is different short circuit values of that different short circuit changes. So it is very important to calculate a particular short circuit current, so that during any fault the circuit breaker has to be open. So they have given some formula also here. The amperes at operating voltage, that is amperes at rated voltage into rated rated operating voltage. So this is the, and interrupting short circuit current, interrupting current is very important. Again they have calculated with using this formulas. Rated interrupted MVA, that is root 3 line into current. Okay, now the main thing we have to calculate is SC, short circuit MVA, that we calculate from root 3 into pre fault line current into SC current in kV. So by using this all formulas, you will be able to calculate the short circuit MVA current, that is interrupting capacity of a circuit breaker. During the fault, it should interrupt. it should interrupt or it should withstand that high current. Some of the high current passes through the circuit breaker. So what happen, it should withstand the the openings of that circuit breaker, or any of the inside part should not melt. It should be able to conduct. That is very important. For that one, for that purpose only, we calculate the rating of short circuit. Rating of the circuit breaker. Yes, short circuit MVA is very important. Should be calculated for the circuit breaker.